In this video, we will be putting all of our observations together regarding rational functions and actually graphing them. So we're going to sketch f at x, where f at x is equal to x minus 2 over x squared minus 2x minus 15. Your first step has to be to factor. Now there's nothing to factor in my numerator, but my denominator is a simple trinomial. You could do crisscross or whatever method you use, and you should have x minus 2 over x minus 5 and x plus 3. And of course, I'm going to write my restrictions. And I know these restrictions of 5 and negative 3 will result in either a vertical asymptote or a hole. In this case, because neither of the factors cancel out with anything in the numerator, both of these restrictions are a result of vertical asymptotes. So we're going to list them. You have a vertical asymptote at x equals 5 and one at negative 3. So I'm actually going to go to my graph here and just label them. So here is 5. And negative 3 is over here. As I go through, I will slowly add my properties on. Next, we want our horizontal asymptote. Because the degree of the numerator is 1 and the degree of the denominator is 2, then the horizontal asymptote is just y equals 0. So I will also draw that in. Next, the intercepts. We know for the x-intercept, y is equal to 0. If I were to set f at x equal to 0, and let's say I cross-multiplied, that would make the denominator disappear because 0 times the denominator is still 0, and then x minus 2 would multiply with that invisible 1. That's why your x-intercepts just come from when your numerator is equal to 0. So when x minus 2 is equal to 0, x equals 2. There's my intercept. So I'm going to go ahead and label that. Now you will notice that that point actually is on the horizontal asymptote. That's going to be our crossover point that we can verify later on. For an y-intercept, we want to set x equal to 0. So we're just finding f at 0. It's going to be 0 minus 2, 0 minus 5, 0 plus 3. You could also do this in your non-factored version. Negative 2 in the numerator, negative 15 in the denominator. So our y-intercept is 2 over 15. As a coordinate, here it is. And I'm just going to estimate that point. If I were to look at my calculator, 2 divided by 15 is 0.13 repeated. So I'm just going to estimate it roughly there. Next, we want to determine our key points. Your key points are going to be to the right and left of your vertical asymptote. So one of our asymptotes is at 5. So I would like to figure out what f at 6 is for the right and f at 4 for the left of that asymptote. And I'm just going into my equation and replacing x with 6 for this first one. So 6 minus 2 all over 6 minus 5 times 6 plus 3. And if I evaluate that, I will get 4 over 9. I can do the same thing for 4. I would have 4 minus 2 in my numerator, 4 minus 5 times 4 plus 3 in my denominator. And give it a try. Make sure you can plug it into your calculator and you do get these values. And I'm just going to plot them. So at 6, we're at 4 over 9. It's a little under half, so something like that. And at x equals 4, we're at negative 2.7, something like that. It's just an estimate. And I'm going to do the same thing for my other asymptote, which is at negative 3. So to the right of negative 3 is negative 2, to the left is negative 4. I'm going to replace x with these values, either do mental math or punching it into your calculator. So again, give it a try and see what values you get. You can pause the video here if needed. But when we put negative 2 in for x, we get 4 over 7. And when we put in negative 4, we get negative 2/3. So I'm going to go ahead and plot that. Negative 2 comma 4 over 7 somewhere there. And negative 4 comma negative 2/3, something like that. Next are crossover points, which I already mentioned. So if our asymptote, our horizontal asymptote is at y equals 0, we want to see if there are any points that cross this line. So I'm going to set my equation equal to that horizontal asymptote, and then I'll see what happens. Now, we already know that there is a crossover point at 2, but I just want to do this to show you the math and in case there are other ones. So I put 0 in because that's the asymptote. And now I'm just going to put the 0 over 1 and do a little cross multiplying. So 1 times x minus 2 is x minus 2. 0 times the denominator is 0. And then when I isolate for x, there's that 2 from before. So 2 comma 0. 2 because it's the answer we just got, and 0 because that's what the horizontal asymptote is. I don't have to plot it because we already plotted it earlier. Final step before we can put it all together on our graph, just connecting our dots and finishing off our graph, is the end behaviors. So there are a few end behaviors we're going to need for this rational function. So I'm just going to start off by making a little table, x, y, and then I'll list out the actual behaviors. The first ones are what happens as x approaches infinity and negative infinity. And you're just going to pick a test value. So as I'm going towards infinity, I'm just going to put 100. It's a manageable number. I'm going to punch it in for x in my equation. So again, that would mean 100 minus 2 for the numerator, and then 100 minus 5 times 100 plus 3. Or I could have gone to the unfactored form as well. But when I do that and give it a try, plug it in, I get approximately 0.01. And me keeping in mind that my asymptote is at 0, 0.01 is above 0, which means as x approaches infinity, y approaches 0 from above. And now I want to see, well, what about on the left side as I get closer and closer to negative infinity? What's happening to my y's? And again, I chose a test value of negative 100. I punch it into my equation for x. And if we do that, we get negative 0.01. That is below our asymptote. So as x approaches negative infinity, y approaches 0 from below. Now, whenever we have rational functions, we also want the end behaviors around the asymptotes, and we have two. We have one at 5 and one at negative 3. So my test values here are going to be points or values for x that are super, super close to the asymptote. So let's start with 5. I'm going to pick 5.01. I want to get as close as I can so that I can see, am I going to positive infinity or negative infinity? I mean, in reality, 5.1 would do the job as well, but smaller the better. And now I'm going to take this 5.01, punch it into my calculator, into my equation, and when I do, I get 37.6. So I am getting more positive. If I did 5.001, so even closer to 5, I'd have an even larger number. But this is telling me as x approaches 5 from the right side, because 5.01 is to the right, y is approaching positive infinity. And then for the left side of the asymptote, I'll pick 4.99. Punch it into my calculator, I get 37.4. So that's a negative number. So as x approaches 5 from the left, y approaches negative infinity. My second vertical asymptote is at negative 3. So to the right of negative 3 is negative 2.99, and to the left is negative 3.01. And again, replace x with these values, see what you get for y. 62.5. So as x approaches negative 3 from the right, y is going up to infinity. And when I punch in 3.01, my calculator spits out negative 62.5, which means as x approaches negative 3 from the left, y approaches negative infinity. And we can take this and finish off our graph. I mean, because of all the key points we used and the intercepts we found, I already have an idea of what this is looking like even without my end behaviors, but my end behaviors will verify this. So I had a point here. I'm gonna follow my asymptotes as a guide. Same thing here. I can't cross the asymptotes in this region because we didn't have crossover points here, and you're never going to cross your vertical asymptote, that's for sure. And then in the center region here, I'm going through my points and then following my asymptotes. And now I can just verify this with those end behaviors. As x approaches infinity, y approaches 0 from above. That's exactly what happened. I'm above. When we approach negative infinity, we're approaching from below, and this is coming from the negatives. Perfect. Check. Around 5, I'm expecting to go up to on the right side, down on the left. Up on the right, down on the left. Perfect. Last asymptote. On the right side, I'm expecting to go to positive infinity. Yes, I am. On the left, negative infinity. Perfect. So if you look at all of these properties one at a time, everything should come together nicely. If one of the properties doesn't check out, it's contradicting another one, that's your clue that you've made a mistake somewhere. So let's try another example. We're gonna graph f at x. There's more factoring to be done on this one, so let's give it a try. F at x equals, we have a common factor of 2. So I'm just going to make a little note here. When I factor out the 2, I'm left with x squared minus 16. So it's not just a GCF, we also have a difference of squares here. So there's my GCF, and when I factor my difference of squares, that's going to be x plus 4, x minus 4, all over, and then a simple trinomial here. So crisscross, whatever method you'd like to use. Gonna do x minus 9 and x plus 4. And what do we notice? The x plus 4s will cancel out. So our simplified equation is going to be just this with restrictions of 9 and negative 4. So our vertical asymptote is the factor that's left, which is x equals 9, but we're also going to have a whole, and this one's going to be at negative 4. To find the y coordinate, we're going to replace x with negative 4 in the simplified function. So that's going to be 2 times negative 4 minus 4 over negative 4 minus 9. That's going to be 2 times negative 8, negative 16. And then negative 4 minus 9 is negative 13. That's 16 over 13. So our coordinate, x was negative 4, y is 16 over 3. Let's find our horizontal asymptote as well, and then we'll go to our graph and label some of these things. So if I look at my simplified function, I have a degree of 1 in the numerator and a degree of 1 in the denominator, which means that we're just going to look at the leading coefficients for our horizontal asymptote. The leading coefficient is 2 and invisible 1. So our horizontal asymptote is just going to be at y equals 2 over 1, or just 2. So I'm going to go ahead and label that. And this horizontal asymptote of 2 is also going to be used for our crossover points. Now, because my vertical asymptote is at 9, I think I'm just going to label on my graph one box is 2. So 2, 4, 6, 8, 10. So 9 is somewhere in the middle there. X equals 9, y equals 2. And I'll also identify my whole. My whole is at negative 4 comma 16 over 13. 16 over 13 is 1 point something. So I'm going to go ahead and plot that. And remember that my scale is 2 units per box. So this is where negative 4 actually is. And there's the whole. For the x-intercept, it's about the numerator. When the numerator is equal to 0, 2 is not going to do anything. X minus 4 will. My x-intercept is 4 comma 0, because that's when the numerator is equal to 0. For the y-intercept, I'm setting x equal to 0, so I'm going to have 2 times 0 minus 4, and then 0 minus 9 in the denominator. That's going to be negative 8 over 9. And those simplify to positive numbers. So I'm going to go ahead and plot that. 0 comma almost 1, but not quite. Now our key points are going to be around our vertical asymptote. The vertical asymptote is at 9, so I'm just going to test the value at 10 and at 8. Again, just punching it into my simplified version. So I would have 2 times 10 minus 4 divided by 10 minus 9. I get 12. So 10 comma 12, that 1, 2, 3, 8, 9, 10. Yeah, that goes off my grid, but I will keep in mind that it's going to be, I don't know, somewhere in the positive region. And then f at 8, so 2 times 8 minus 4 over 8 minus 9, and we get negative 8. And this one will fit. And there it is. See, I already have 3 points on the left side, so I already have an idea that this is going to connect like this around the asymptotes. But I am going to check my crossover points now. Our horizontal asymptote is 2. We want to see, do we cross the horizontal asymptote? So I'm going to set my equation equal to 2. I'll put that over 1, and then I'll cross multiply. So 2 times x minus 9 would be 2x minus 18. And then 2 times x minus 4 times 1. I'm just going to distribute that 2 in. There it is. Now, when you see this, you might already be seeing a red flag here. But if we don't, let's say I were to bring variables on one side, constants on the other. 2x minus 2x is 0x. And then negative 8 plus 18 is 10. And 0x is just 0. So we come to this false statement, 0 equals 10. No, it does not. No, it does not. This is a false statement. Because it is false, this just concludes that, oh, there actually aren't any crossover points. So here we are. I already have an idea, like I said, that this is going to connect like this. So I already have an idea about my end behaviors. Below 2 towards negative infinity. And I'm thinking my other arm will be here because we did have that point up in the positives. But we're going to do our end behavior test just to be certain. X, Y. So long range. So as x approaches infinity and as x approaches a negative infinity, I'm just plugging in 100 and negative 100. When I plug in 100 for x, I get 2.11. Our horizontal asymptote is at 2. 2.11 is above, so that means y approaches 2 from above. When I plug in negative 100, I get 1.91, which is less than 2, so y is approaching 2 from below. Then my other two end behaviors are going to be around the vertical asymptote. It's at 9, so if I'm testing to the right of 9, I'll use 9.01. So as x approaches 9 from the right, if I want the left, I'll use 8.99. And now let's see what happens to y. I have an idea based on what I'm seeing on my graph, but this will verify it. I put 9.01 in for x in the simplified equation, and I get 1002. Yep, y is definitely going to positive infinity. I plug in 8.99 and I get negative 998. Y is going to negative infinity, which I was predicting based on the points I saw. Now I can just connect my dots and be confident that everything worked out and there are no contradictions. Now, if I did want some accuracy on this side, because the only point I have is off my grid, I can definitely plug in other points. Like, I don't just have to plug in 10. I could try plugging in 12, see what's going on here. But I'm just going to follow my asymptotes. And there's function f at x. A vertical asymptote, a horizontal asymptote, and a hole. And these are the steps you're going to use for every rational graphing to decide what discontinuities there are, where the intercepts are, if there's any crossover points, finding your key points and your end behaviors.